Swayam Prabha. Digital India. Educated India.
Welcome to this course on transition metal organometallics in catalysis and biology. Today we are going to be talking about oligomerization of alkenes and alkynes. This is an interesting area which has emerged out of Ziegler-Natta catalysis, and it has its own domain. Now we have discussed these alkene and alkyne oligomerization reactions earlier in the context of applications of organometallic catalysis in large scale synthesis. In this context, it is worth noting that we have spoken about important industrial process which is called shell higher olefin polymerization process, which was developed in 1950s to make use of various fragments of alpha olefin oligomers for commercial purpose. Now, the story is sort of goes back to 1950s when Shell was trying to develop methods for using alpha olefins from the range of C8 to C14. So, we had discussed this in great detail in our earlier lecture on various applications of organometallic catalysis, and a nice review of this process shell higher olefin process or SHOP has been nicely reviewed in this article by William Keim. In Anguchem internal edition in English 2013 52 12492 to 12496. We have looked into this process whereby alpha olefins were prepared by Ziegler-Natta method C2H4 ethylene using nickel catalyst produced alpha olefin oligomers, and that had a huge distribution as is shown over here of different fragments. Mole percent from C12 to C18, and this is greater than C18 and this is less than C12, and the distribution goes something like this, of which the range of alpha olefins from C12 to C18 this range was used for making detergents. and this was what provided the impetus for looking into use of the other two fragments which at that point of time were not being used. One is the fragment which was less than C12 and the fragment which is above C12. So, these fragments at that point of time were unusable and were trying to find some use to make these unusable fragments. Now, this oligomerization of alpha olefin was produced by this process which is called alkene oligomerization. Using Ziegler-Natta catalysis. That means that coordination insertion method. So, all these alpha olefins, the whole thing was produced by this process of having have to use nickel catalyst for alpha olefins, but of these various fragments only the usable fractions was C12 to C18 was usable. Now, in this shop a parallel development in which they used isomerization reaction as well as metathesis reaction to use these fractions C12 and C18 to convert to around something between C12 to C18 and hence can be utilized. So, this was done using Ziegler-Natta catalysis, and a nice example is given over here in the following reaction. For example, one octene, this is C8, was isomerized to give the isomerized product which is 4 octene as well as CH217, this is 1 eicosine, this is C20 fragment isomerization to give eight to get 10 eicosine, and these two together was done metathesis to give C10 or 2 tetradecene. So, what we have seen that this shop includes three process mainly. The first is this coordination insertion process, coordination insertion process. This is number 1 process which generates all these this range of alpha olefins generated from here, and then the 2 other process, one is isomerization process over here as well as over here, isomerization process, and the second one is metathesis process which is over here. So, these 2 processes together would help these fractions which are less than C12 and C18 together to come into a range which is usable. So, for detergent purpose. So, mainly a couple of processes that came together to look at to find use for this wide range of alpha olefin as a part of the Schwab process. Now, in our discussion so far, what we have done is we have already discussed these reactions earlier on, isomerization as well as metathesis as well as this distribution curve as a part of olefin metathesis while covering the utility of olefin metathesis in industrial scale. And however, we have not looked into this oligomerization process using nickel catalyst, and in today's lecture we are going to focus on this alkene and alkyne oligomerization using Ziegler-Natta catalyst as a part of the Schwab chemistry, and all of it is nicely reviewed by this William Keim article given in Angio KM 52 12492 to 12496, and I request all the students who are auditing to this course to go through this review which is which explains the story and the development at that time very elaborately, and would benefit the reader very much. So, shale higher olefin process, characteristics, one it involves the formations of C8 to C18 from ethylene based on oligomerization, isomerization, and alkene metathesis reaction. Now, this we have discussed in detail in our previous slide where we had shown you diagrammatically where with example where each of these reactions play a role to produce this C18 to C8 to C18 fragments which are which had application for detergent usage. So, these 3 reactions are to be discussed under the Schwab cell higher olefin process reaction family of reactions. Now, the other characteristics of Schwab is the Schwab process is the most successful method in industry under homogeneous conditions. And usually these polymerizations are carried out in polar solvents. So, this is one of a powerful method in which this oligomerization reactions to produce alpha olefin using Ziegler-Natta catalysis is concerned. So, SHOP is a very successful method in industry and it was primarily used for producing alpha olefins from ethylene as an alternative method for producing alpha olefins from petroleum or by cracking of natural and crude oil. So, let us now take a look at the mechanism for this alkene and alkyne oligomerization reaction. Mechanism. Now, the rule of thumb is that if it is electron rich metal, then oligomers are preferred, whereas if it is a electron deficient metal like early transition metal, then these polymers are preferred. So, for Ziegler-Natta catalysis, the rule of thumb is for MXN XN type catalyst, M equals electron rich late transition metal then oligomerization oligomerization is favored, giving alpha olefins, whereas when M is electron deficient, early transition metal, then polymerization is preferred. Now, in our first discussion on the extent of the growing of the polymer chain, we had said that the extent of this chain length is very much dependent on the rate in which this the propagation step and the termination step they occur in a comparative sense. If propagation step is faster than the termination step, then one ends up getting polymers, and if the propagation step is comparable or slower than the termination step, then one ends up getting oligomer. And also what we see that this for electron deficient metal, early transition metal polymerization is preferred, implying that the propagation rate is higher than that of the termination step, whereas for electron rich late transition metal the propagation rate is comparable or slower than that of the termination rate. One can implying that alpha olefin oligomers are formed. Now, we are going to take a detailed look at the mechanism of this oligomerization reaction. So, this is the catalyst. So, these loses the hydrogen in a beta hydride elimination process. This is alpha carbon, this is beta carbon. In a beta hydride elimination process, giving an active species of nickel hydride along with nickel cod chloride. So, cod is eliminated and the active catalyst is formed. So, this is the active species which then enters the catalytic cycle, and this is represented by this cartoon diagram. As is shown here. The nickel hydride then reacts with the olefin by coordination insertion pathway. This is the coordination. So, coordination step, and this is the insertion step. As is shown here. And now, this olefin moiety will insert into the nickel hydride bond, creating a vacant site as is shown over here, and a nickel ethyl moiety. Now, a second olefin will come and bind in the olefinic site, coordination followed by insertion as is shown in the previous step. Now, this can proceed in two directions. From here, the first is that it can beta eliminate, as can be shown over here. This is alpha, this is beta. It can beta eliminate to give the catalyst nickel hydride coordinated to the alpha olefin, which can eventually give the nickel hydride species and the olefin going away. And the other method is over here. Another olefin can come n times, bind in the vacant site n times and undergo coordinative insertion, coordination insertion to give a nickel alkyl species, and this nickel alkyl species can beta eliminate to give the nickel hydrogen along with alpha olefin, long chain alpha olefin. And these alpha olefins through isomerization and olefin metathesis is taken for producing the desired fraction by Schwab process. So, what it shows that these oligomerizations are mainly proceed by two methods, which is coordination insertion, and in the Schwab process the late transition metal nickel is used for olefin oligomerization, and usually the active sites is a nickel hydride species is the active complex. Now, nickel hydride species can insert olefin and then coordinate olefin and then undergo insertion. Then it can do the same thing twice over, and then there is a possibility, in the first possibility it gives 1 butene and a nickel hydride, or it can undergo subsequent olefin insertion to give a long chain nickel alkyl, which can then beta eliminate to give back the nickel hydride as well as alpha olefins. Now, these alpha olefins are then fed into the isomerization and olefin metathesis reaction as a part of the Schwab process. So, with this we conclude our discussion of olefin oligomerization as a part of Schwab process in today's lecture. And what we have done, let me recapitulate. What we have done is we have looked at the shell higher olefin process in its entirety, and we have looked at how 3 different applications of organometallic chemistry involving this alpha olefin oligomerization reaction using nickel catalyst, and second the isomerization reaction, and third the olefin metathesis reaction all come into play in channelizing the various lengths of alpha olefin obtained for producing something which is important commercially, particularly the alpha olefins in C8 to C18 fractions which are used commercially. So, with this we come to the end of today's lecture. We are going to be taking up more on olefin oligomerization when we continue with the discussion in the next lecture. I thank you for being with me in this lecture, and I very much look forward to being with you in the subsequent lecture when we talk more on olefin oligomerization reaction in more detail. Till then, goodbye and thank you.